My name is Yarel Maman, and I'm a backend engineer at Mobility. Today we're going to talk about Go secrets and gotchas. A little bit about myself. I've been writing code in Go for a couple of years now, since Go 1.5. Coming from a background of mostly C and C++, I find Go to be refreshing, productive, fun, but most of all simple. So to begin our journey, let's walk down the path that I think many of us went through once we started learning Go. First, you probably completed the tour of Go. By a show of hands, who here has completed the tour of Go in the last year? Okay, that's quite a few. Welcome. Then, some of you may have read Effective Go and start to grasp some idioms of the Go language. So when I was at that point, just started learning Go, I quickly developed the notion that Go is simple. And I still think it is. Go is designed to be simple. I mean, you can actually read the entire language spec and stay alive to tell about it. This is not trivial at all compared to some other programming languages. And I think it really comes to mind when you explore Go code written by others. I think that many times the simplicity of the language creates a very readable code base. And I will quote Rob Pike by saying, readable means reliable. That being said, over time I began to notice some more interesting things about the language, some hidden secrets. Now these aren't really secrets, they are documented. I call them secrets because many times the reasoning for them lays in the internals of the language or the runtime. So sometimes knowing a bit about how things work behind the scenes is key for foreseeing the possible pitfalls and understanding them. So I thought, let's shed some light upon a selected few of them, a few which I think are very common, especially amongst beginners with Go. Then it might get easier for us to notice them, hopefully before they become nasty bugs. We'll start by going over some pretty basic details about the language. To begin, I want to start with a basic fact about Go. Everything in Go is passed by value. Now, what that means is a function gets a copy by value of the thing being passed to it. You pass an integer, you get a copy of the integer value. You pass a struct, you get a copy of the struct value. You pass a pointer, you get a copy of the pointer value, which is a memory address it points to, but another copy of the data it points to. This is different from passing by reference, where you share the same variable with the caller. You may be familiar with passing by reference in other languages, such as C++. Go doesn't support it. But what about slices, maps, interfaces, and other types? Let's start with a small example. So we have a function, append to slice, which gets a slice and appends the number 2. And in our main func, we print the slice contents before and after calling this function. Alright, so let's run it. Notice how slice didn't change, it stayed empty. We will see why soon. Let's now see something similar, now with a map. So we have a function which gets a map and sends some value as a supplied map. And once again, we print the contents before and after. Let's run it. Alright, now the map was changed. So what's the difference here? Let's talk a bit about slices. So a slice behind the scenes is a struct with 3 fields. The first one is a pointer to the backing array of the slice, which holds the slice contents. The second is length, is the current length of the slice. And the third is the capacity of the slice, which means how many items the backing array can hold. You can think of a slice as a view or an interface to an array. So every time you pass around the slice, you're actually passing around and copying the struct. Now keep the struct in your head. Every slice operation you do will relate to this struct. So a map, as opposed to a slice, is actually a pointer behind the scenes to an internal hmap struct. Now you don't see that pointer, but when you're passing around the map, you're actually passing around a pointer to hmap. And when you access or modify a map, a pointer is the reference for you. Now going back to our example, append slice gets a copy of a struct and modifies the call struct. But that didn't affect the call of the slice struct, which stayed the same. Set map we got a copy of a pointer by a value, and the action of setting the map's value dereferenced that pointer. So we actually accessed and changed the caller's map. So while we still talk about maps and slices, here's a fun one. We have a simple struct called item, and then we initialize a map from int to item, and then we try to change struct field ID in the map value. Alright, so we try to compile it, but oh, it does not compile. We get a compile error, cannot assign to struct field in map. Slice values, on the other hand. Sorry. Okay, why is that? First, we try to change a field inside a map value. So to do that, the compiler will need to fetch the address of this map value. But in Go, map values are not addressable. Now, slice values, on the other hand, are addressable. So in this case, the compiler can fetch the address of the slice value, and the same assignment is allowed. Now, personally, I was intrigued on why do we have this restriction on map values. And I discovered this restriction is in place probably because of the map's implementation. So in Go, a map is actually a hash map, and the hash map is composed of hash buckets where the map values are stored. So when the map grows, values may be copied from one bucket to another, and at some point, old unused buckets may get dropped. So if you hold a pointer to a map value for some time, there is a risk of accessing an old invalid bucket. That's why it's restricted. But in this case, we do not aim to hold the pointer, just use it for this assignment. So there's actually an open proposal issue to change the spec to allow this kind of behavior. But currently, to get around that, either you read the value to a variable, change it and set the map, or change the value type to be a pointer to item. That would work as well. Just make sure you don't dereference a new pointer. So what's slicing slice? Slicing does not copy the slice's data. It creates a new slice that points to the original array. So in this example, we have a slice of length 5, and we slice it to get the items from index 2 to 4. So we get a new slice struct that points to the same array. So that was a really short intro to our next case, memory leaks when slicing. So you might ask yourself, isn't Go a memory managed language? Yes, it is. However, with slices, you can reach such a situation when you have data which you don't need anymore, but it might not get garbage collected. Let's see an example. So we have a function called findDigits. It gets a file name as an argument and returns a byte size. Now the purpose of this function is to find the first consecutive group of digits in the file contents and return it as a result. So let's run it with some imaginary file. Let's debug it. Our example file, contents, starts with 2 consecutive zeros, and then it's just A letters all the way to the end of the file, and the file size is 3.7 megabytes. Okay, so first we call read file, which reads the entire file contents to a byte size. Now let's look at the slice header returned by read file. Data points to a backing array. Length is the length of the slice, which is actually the size of the file. And then we have the capacity, which is a bit above the length. So then we pass b as an argument to the find method. And the find method returns the first group of the regex match by slicing its argument, b. So the return slice header of find looks like that. Data points to a backing array, once again, but you can notice it is the same address as our previous slice header. And length is now 2, because it only returns the first 2 zeros that we have in our file. And the cap is also as the previous slice header. Now, what happened here? So, our previous slice was sliced again by the find method. We still use the same backing array of the slice, which holds the slice contents, the file contents. But the new slice length only covers the first 2 bytes of the array. So the issue here is these 2 digits are only a small part of a pretty large file contents array. We don't really need the file contents in our memory anymore. But when the garbage collector will go over the file contents array, it will notice it is still referenced by a result slice and will not free it. So a possible solution to that we can just make sure the file contents array isn't referenced anymore. So we'll just allocate a new buffer with a reduced length and copy our ticket slice result to it. And by that, we got a new slice header, which points to a different backend array. And this backend array only holds these two zeros that we want. So after the function ends, the file contents array will no longer be referenced, so eventually it will get garbage collected. Alright, enough talking about slices, let's move on. So here we have another case. First we declare a pointer to integer called counter, and we compare counter to nil. And the output of that is true. And then we declare an empty interface called metric, and we compare to nil. That is also true. And then we assign counter into metric, and we compare metric to nil. That is false. That means metric does not equal nil. But why is that? Didn't we just assign the nil value to metric? To understand why, first we need to understand how interface values work. So, an interface value is actually composed of two dynamic parts. First we have the dynamic type, which is a type info of some type t, and t implements the interface. And the second is a dynamic value, a copy of a concrete value of type t. So when you assign to an interface variable, these two parts are filled implicitly. In our case, the metric variable. Why are these called dynamic? Because these can change at runtime. We are used to values that change at runtime, but now the internal type of a variable can change at runtime. So let's go back to our code example. But now, we print the dynamic type and value of the metric variable before and after the assignment. So as you can see, before the assignment, the dynamic type and value are both nil. After the assignment, the dynamic type is a pointer to integer, and the dynamic value is nil. So to finally understand why metric does not equal nil, we need to be aware of the following. An interface value is nil only if the value and type are both unset. So let's go back to our example again. You can see here that after the assignment, the dynamic value is unset, it's nil. The dynamic type is a pointer to integer. And that's why metric does not equal nil. Let's see a case where this gotcha is quite more common. You might be familiar with this example when handling errors. So here we have a function which returns an error. We declare a variable p of type myError, and this type implements the error interface. And then if something bad happens, we assign some error to p. And then we return p. Quite simple. So at first you might expect that when nothing bad has happened, we'll return nil as an error. But we'll actually return a non-nil error each and every time. And that's because error is an interface, and once again, we assign a dynamic type to it, which makes it non-nil. A possible solution to that is just to declare our internal error as the error interface type. In this case, when all is well, we'll just return its zero value, nil interface. So in general, be aware with returning custom error types as an error interface. We'll stop talking about nil here, but I'll just say that there are more funny issues with nil, and if you're interested, I really recommend watching Franz Kampoy talk, Understanding Nil. Let's see something else. Here we have a slice called values, slice of integers from 1 to 4, and then we range them over these values. And on each iteration, we spawn a routine which prints the value and the address of the value. Now, you might expect the first routine to print 1, the second 2, and so on, not necessarily in the same order, because it's up to the scheduler. But we run it, and that's not what happens. Notice all routines print 4, and the disturbing part is that they all print the same address. What's going on here? Well, this is a language design issue regarding range loops, which states that each loop iteration uses the same instance of the variable val. That means each routine closure shares that single instance with the other routines. You can see that by the fact that they all print the same address. It's the same instance. One way to deal with it is to pass val as an argument to the closure function. So now each coroutine's got a separate variable, and each one's got a separate address, like we want. So another odd solution, in my opinion, is to write assign val to val. This solution appears in effective Go and in the Go FAQ. And why does this work? Because very much like the previous solution, we now shadow the variable val with a new variable, which also happens to be copied. So each coroutine gets a unique variable. But I would say this is a bit confusing. By the way, there is also an open proposal issue for changing this behavior for Go to redefine range loops variables in each iteration. And you can use GoVet to get our notes on this specific behavior. Just run it against your source file. So while we are at loops, here's another case. Here we are ranging over a channel in a loop. And on each iteration, we open a file. Now, maybe you can relate to this feeling. I really like defer. And when I'm opening a resource, I have the urge to immediately defer close it. But we have to keep in mind that the first statements are only executed when the function scope ends. So in this case, you may end up having a lot of open resources for no good reason, and perhaps for a very long time. So be careful when deferring inside the loop. In this case, you can just close this resource at the end of the loop, or move this logic to a separate function. Let's talk a bit about cases related to the standard playlist. So Go sync primitives must not be copied. On the right, we have the definition of the mutex from the sync package. It is composed of two numeric values. When you copy a mutex, you actually fork its state, and you're creating a separate lock, which makes no sense, really. So this applies to all of the sync primitives. Always pass them by address, and don't copy them. And types containing sync primitives, values, must not be copied. So in this example, we have a struct called value, and it embeds an RW mutex. If you copy the value, you also copy the mutex. This example illustrates a bug, which I think is quite common. This bug may be tricky. I would like to start with a short story. So there was something quite similar to this piece of code in a code base that I worked on. We had this running for a while. Tests passed successfully. Docs were added successfully. Sorry. And we had no visible side effects. Happy days. At some point, we started to experience panics related to this map assignment. It turns out that until then, this method was called from a single Go routine. But at some point, multiple Go routines started calling it concurrently. And that's what triggered the side effects of this bug. Okay, so you might have guessed, or you might have just saw it. The bug is here that we're using a value receiver, not a pointer receiver. A value receiver means that this receiver pond will get copied each time addDoc is called. So by copying pond, you also copy the mutex, and we've already seen that copying the mutex is a bug. Now the lock is useless, and we have no protection. How come we didn't notice it before? How did we manage to change the map if we used a value receiver? Well, remember that we said that a map is actually a pointer? That's why it worked. And why do we get a panic? We will see why over the next slides. On this case, you should use a pointer receiver. And most times, my default action is to use a pointer receiver, since it's common for methods to modify the type that they are defined upon. And for that, you need a pointer. But in some cases, it makes sense to use a value receiver. So there's actually an awesome wiki page on when to use each. And beyond that, it's called Core Review Comments. If you don't know that, you should check that out. And you can use GoVet to detect this as well. So we've seen two gadgets that GoVet can easily track, which makes it pretty useful. Let's move on. So Go built-in maps are not safe for concurrent write or concurrent read and write. So let's see an example of concurrent read and write. So here we're trying to read from one Go routine while writing from other Go routine with no protection. So this is a data race. However, concurrent read-only is safe. So here we write to a map, and then we're sure that all Go routines are only going to read from this point now on, so no protection needed here. The runtime enforces safe map access, and might panic if violated. Here we see an example of a panic caused by concurrent map writes. Remember the previous example with a lock and a map? Well, this is the panic we got there. This panic might be rare, so don't rely on it to track all of your data races bugs. When needed, use the appropriate synchronization primitives from the sync package. Sync.map is safe for concurrent use. However, you have to be aware that sync.map is optimized to fit certain use cases, which are described in its documentation, and you lose compiler type safety by using it. So most of the time, you'll be better off with a regular map and a lock. The Go data race detector is a very cool feature built into the Go toolchain, which can help you to track data races, such as this. Bottom line, it will tell you of a data race and the exact line that caused it. So if you find yourself idle at work and just looking for some tasks, just run it. You'll be busy for a while. Just kidding. Run it locally, run your test with it, make it a part of your CI infrastructure. It has no false positives, so you should fix all of the data races that it reports. This is a runtime feature, so you have to compile and run it with your binary. It won't find all of your potential data races, just the one that actually occurred at runtime. And this is a development feature. Don't ship it for production. It comes with performance penalty. So that was just a teaser. We've seen only a small part of possible gotchas and pitfalls you could encounter. My real goal here is to get you a step closer to the real deal, which is being more aware. So how do I do that? The ultimate way for awareness, in my opinion, is just reading the source. When I reach a part of the language that seems unfamiliar to me, I personally like to go to resources like reading the package docs. Many times the information you need is just there. Read it carefully. Read the Go spec. Don't be afraid to dive in. It may seem tedious, but just focus on a specific subject. You'll be fine. Reading the Go source code. It's written in Go. How cool is that? And it's one of the best places to learn Go, in my opinion. Next thing, experiment. So you encounter the behavior you're not familiar with. Don't dismiss it. Take the opportunity to fire up Go Playground, write a test, and just run some experiments. And if you discover something really cool, don't keep it a secret. Share the knowledge around. And if you do a code review, which I really hope you all do, don't miss out on potential gotchas. Sure, it's probably written somewhere, but you only truly learn it when you experience it yourself and understand why it happened. The last part, but not the least, is to stay attached to the Go community. So things like keeping up to date with the language development, especially now with Go 2. Reading Go GitHub issues. Reading the changelog of new Go releases. Subscribing to newsletters such as Golang Weekly and others. Reading the Google group Golang Nuts and subreddit Golang. These things will help you keep you up to date on the important things and less surprised about future gotchas. One of the fun parts in Go, in my opinion, is that it feels like the language is in a constant change and improvement phase, and the Go community is really an active part of this. I hope you learned something new. Thanks for the opportunity to be here.